Hey everyone, we use averages all the time to make sense of the world. But what if I told you that the average often hides the most important part of the story? Today, we're going to look past the average and explore the concept of spread and why it's the key to really understanding what your data is telling you.
So let me just ask you this right off the bat. Can two groups of numbers have the exact same average, but tell you completely different things? The answer is absolutely. And figuring out why is what this is all about.
Okay, check this out. We've got two teams. Team A is super consistent, right? Their players score a 4, a 5, and a 6. Then you've got Team B, who are kind of all over the place with a 1, a 5, and a 9. Now here's the crazy part. The average score for both teams is 5, exactly the same. But are they the same team? No way. Team B's scores are way more spread out. And that difference, that spread outness, is exactly what we need to measure. Luckily, statisticians have a whole bunch of tools designed specifically for this to help us capture the story that the average completely misses. And here's the official kind of fancy name for them: dispersion parameters. Don't let the name scare you. It's really just a set of tools that measure how much our data is scattered around that central point, like the mean. They just answer a simple question: are all the numbers huddled together, or are they spread far and wide? So think of this as our toolkit for the job. We're going to open it up and look at the three main tools we use to measure spread: the range, the interquartile range, and the big one, standard deviation. Each one gives us a slightly different angle on the data.
All right, let's start with the simplest tools in the box. These are the ones that are super intuitive, the ones you can practically figure out just by glancing at the numbers.
First up, we have the range. And yeah, it's pretty much exactly what it sounds like. It's just the distance between the very lowest value and the very highest value. In one quick calculation, it tells you the total end-to-end spread of your data.
This picture just makes it so clear, right? If you want to find the range of heights here, you just find the tallest person, find the shortest person, and subtract. Boom! That's your range. It's the full variation from top to bottom. Super simple.
But, the range has a bit of a weakness. A single outlier, like one person who's 7 feet tall when everyone else is around 5 feet, can make the range massive and misleading. So, what if we want to ignore those extremes and just focus on where most of the people are?
Well, that's where quartiles come in. Just imagine you take all your data points and line them up in order, from smallest to largest. Quartiles are just the markers that chop that line into 4 equal chunks. And that second quartile, Q2, the one right in the middle, you already know that guy. That's the median.
And that brings us to a much more powerful tool, the interquartile range, or IQR for short. This is a game changer because it focuses only on the middle 50% of the data. You just take the third quartile and subtract the first one. By doing that, it completely ignores the weird outliers on either end, giving us a much more stable idea of the typical spread.
Now, the absolute best way to see this is with something called a box plot. You see that box right in the middle? That is the interquartile range. The bottom of the box is the first quartile, the top is the third. So that little box literally shows you where the core 50% of your data is hanging out. It's pretty cool.
And if you look even closer, there's more info packed in here. That solid line inside the box, that's our median, slicing the data perfectly in half. And the dashed line, that's our old friend the mean. This is why box plots are so awesome. They show you the center and the spread all in one simple picture.
Okay, so range and IQ are super useful for sure. But the true powerhouses, the ones you see everywhere in science and finance, are variance and standard deviation. And their secret is that they don't ignore a single piece of data. They use every last point to figure out the spread.
So let's start with variance. Now what it does is measure the average of the squared distance of every point from the mean. And that word, squared, is super important. It's a math trick that makes everything work out nicely, but it leaves us with units that are kind of hard to wrap your head around, like square centimeters. What even is that? And that is exactly why we have its much more famous sibling, the standard deviation. All it is the square root of the variance. By taking the square root, we get rid of that whole squared problem, and we're back to our original units. So it gives us a number that tells us the typical distance any single data point is from the average. It just makes sense. This slide just lays it out perfectly. The average height here is 155 centimeters. The standard deviation is 11.5 centimeters. So what does that number actually tell us? It means that a typical person in this group is about 11.5 centimeters taller or shorter than the average.
It's just a beautiful single number that sums up the consistency of the whole group.
So let's just break it down one more time. Variance gives us this number in weird squared units. It's super important for the math behind the scenes, but it's tough to interpret. Standard deviation takes that number and translates it back into plain English, into units we actually understand, making it perfect for explaining what's going on.
And here you can see the relationship in action. You have the formula for variance, which looks a little complicated, but then you just take the square root of that result and you get the standard deviation. One flows right into the other. It's all about turning a mathematically useful number into a practically useful one.
Okay, so we've got this awesome toolkit for measuring spread. But so what? Why does any of this actually matter out there in the real world? Why should you even care?
Well, it matters because it's literally everywhere. In finance, a stock with a high standard deviation is seen as volatile and risky. In a factory, a low standard deviation for a product means your quality control is amazing. When testing a new drug, the spread tells you if it works on everybody or just a few people. From weather forecasts to sports analytics, understanding variability is everything.
I really love this quote. It just nails the whole point. The average tells you the center of town, but the spread tells you if that center is a tiny village where everyone lives close by or a giant sprawling city. A small spread means that average is a really good description of the group. A huge spread means that average might not really describe anyone at all.
So, I'll leave you with this to think about. Your daily commute. You probably have a rough idea of the average time it takes, right? But what's the spread? What's the standard deviation? Is it only 2 minutes, or is it more like 20 minutes? Because that number, that spread, is what really determines if your morning is predictable and calm or a totally stressful gamble every single day. And that's a perfect example of why the average alone is never, ever enough.